Okay, and welcome again to finally part 3 of our webinar series on amplifier additive phase noise testing at mini circuits. And I just want to thank all of you who have actually gone through parts 1 and part 2, and to kind of repay you for taking the time and effort. I'm going to skip through or breeze through some of the introductory material here. So if you've not watched part 1 and part 2, that will be some motivation to go back and watch them. For those of you that have, I won't make you suffer through my explanation again of our test set. So part 1, again, we talked about what is additive phase noise, how we measure it specifically here at mini circuits, and how to specify it. Won't go through that again. Part 2, we looked at cascaded amplifiers, specifically what I'm calling LO amplifiers, amplifier cascades that would be used to drive the LO port of a mixer, for example. And we looked at how it's possible to optimize input powers into both first and second stages for a series cascade so that we minimize or mitigate the effects of AM to PM distortion. We know AM to PM distortion, when expressed as a degree per dB, has a very characteristic shape. And we want to avoid that peaking, that region where the AM to PM distortion peaks. And by careful selection of power levels, we can actually accomplish that. We looked at a series configuration, and we looked at 4 amplifiers and a parallel configuration, but in part 2. But unfortunately, we couldn't really see the full benefit of paralleling the amplifiers because we were noise floor limited. What we're going to do in part 3 is we're going to have a single stage drive the 4 in parallel. So if you just think about it theoretically, I should get a 6 dB improvement in the 1/F from the 4 in parallel. And I'm driving that with a single. I should kind of see the performance of the single. Okay, that's really what we hope to demonstrate here. And we'll look at, again, 2 different cases, 2 gigahertz and 6 gigahertz, because two different regions, because the AM to PM distortion for both of those carrier frequencies is very different. And if we're designing a broadband amplifier cascade, we need to consider that across the wider band. So again, those are our 2 reference frequencies that we've been using. We're going to continue to use 2 gig and 6 gig as our examples here. I will, again, for those of you, thank you who've watched part 1 and part 2. I won't spend a lot of time here. You've seen this before. This is our additive phase noise test set. All the precautions and what things that you should follow for best results are all listed here. I won't repeat them. What we focus on and what we're very careful about is the signal source output power from our analyzer, because the additive phase noise performance will vary. It will be different depending upon what carrier level and what carrier frequency you select. So we need to make sure that for each carrier frequency under test, we make sure that we can find a signal source output power level that gives us the best overall response. Very important. And again, we always try to come back into the analyzer over a fairly narrow range so that it makes the measurement more repeatable and more consistent. We do that with our combination of mechanical and fixed attenuators. And again, go back, read part 1 and part 2, or go back and look at part 1 and part 2. You'll find this will repeat it there in more detail. Okay, so again, as with part 2, we're going to focus now on cascaded configurations, but we're going to do a single device feeding 4 in parallel. It's not on this chart, courtesy of Professor Rubiola, but it will be a cascade of a single driving 4 in parallel. And again, we're going to look at different operating regions, different power levels inputted to the first stage and the combined 4 stage. And we're going to see what differences, and can we find, again, a configuration that allows us to achieve optimum additive phase noise performance over a wide band. Again, we always start with our test set noise floor, because that's ultimately going to limit what we can demonstrate and what we can measure to. So we have it measured here again at 2 and 6 gig, 2 gig and 6 gig, which are our reference frequencies for this webinar. The stars will be repeated on a lot of the measurements that you see of the amplifiers because we want to get an idea where is our noise floor. So we're going to start out with now a little bit different. You see here the single stage. Here we have a 0 dB pad driving the 4. So it's literally one stage driving 4 stages without any real thought to optimizing power levels. We're just going to go for, say in this case, maximum output power. So actually, if you're looking for a 1 watt amplifier, 2 gigahertz, this is not a bad combination. We use our reference LVA 273PN. It's just in a ZX60 connectorized configuration here. So again, here, this is the input power into the first stage. This is what comes out of the first stage. It gets divided or split with the 4-way. This is what goes into the second stage. This is what comes out. And then this is what gets combined as a final output here. So this case is of interest because notice we're going from +1 to +12. Look at that. No matter what the carrier frequency, we're going right through that region of peak AM to PM distortion intentionally. We want to see what happens when I drive into this region. Maybe nothing. Let's see. The output stage is saturated, so we're well off the chart here. We don't have to worry about him. But the first stage is going to be dominating our performance. Let's verify that because we're running right through this peak region here. Okay, so we, as in part 1 and part 2, we always start with our single stage and look at his performance. And again, it's mostly noise floor limited, except at the higher offset frequencies over the power level that we just showed. There's our single stage. This is from part 2. We saw this is what the 4 combined looked like. Again, mostly noise floor limited, so we can't really demonstrate the 6 dB improvement when we look at this as just a parallel configuration because we're noise floor limited. But now we're going to drive the 4 with a 1, again, to 0 dB pad. And what do we see? Again, at 2 gigahertz, we have a lot of freedom to choose power levels because we're not really influenced by AM to PM distortion. So again, if you want a nice 1 watt amplifier at 2 gigahertz, this is not a bad way to achieve that. And look at this. You're basically not seeing the degradation from the 4 combined amplifiers, the 4 parallel combined amplifiers, which is what we said. We're gonna see that they don't degrade the performance because we're gonna cascade it with a single. And what do we really see? Basically, the performance of the single stage here. So from that, we can infer that this combination is really not degrading the cascade, and it's being set by the performance of the first. So are these power levels optimum for anything? Well, at 2 gigahertz, like I said, we have a lot of freedom there. Let's look at 6 gig and see what happens. So now, same configuration, same 0 dB pad in between, same input power range, output power range. We're going right through the peak of AM to PM distortion from the first stage. The second stage is still kind of off the chart here, so we expect our degradation to be coming from the first stage. Let's see what happens. Again, here's our reference. Here's our single stage by itself. Here's the times 4 by itself. Now we're going to cascade them. What happens? Oh, look at that. That hurts, right? Look at the degradation we're seeing in the 1/F noise region, in the flicker noise region, because we're transmitting, we're transiting through that high AM to PM distortion. So since these tick marks are basically the single stage, you can go back and forth. You can see we're taking a pretty big hit in additive phase noise, really because of a poor choice of input power. So what can we do about that? Well, we can change the input power range. That's easy enough. And we can change the power level into the four parallel combined by using a pad, like we did in part 2. Are we going to get the same output power? We're going to be pretty close, because don't forget, we're saturating the heck out of this. So by pulling that out of saturation, like we did in part 2, replacing that loss with a pad, we're not changing the output power that much. Okay, so you can trade that off. So it's possible to trade off output power versus a pad here and lowering the input power here to get out of that high AM to PM distortion region. So let's see what we can do here. Here's again our summary that we presented during part 2, so you can see what happens single stage versus the 4 at 2 gigahertz, basically the same. At 6 gigahertz, again, basically the same. No real difference because we're limited by noise floor for the 4 combined case. If we go now to single versus the single driving the 4, what do we see? Well, again, at 2 gigahertz, we don't see AM to PM distortion effects much, so the performance is roughly the same. So the performance here is about the same as the performance here. I'm not adding much, if anything, by cascading it with 4 parallel amplifiers. Not the case at 6 gigahertz. Why? Because again, we're driving this guy incorrectly. He's dominating our performance now, so we want to change that. Can we? Let's find out. One more comparison here. Apologize. 2 gigahertz versus 6 gigahertz. We're comparing against what we did earlier with the 2 stages in cascade, again with the 0 dB pad here. So at 2 gigahertz, look at this. This is really insightful because you are getting much better performance, 1 driving 4 versus 1 driving 1. So this is good evidence that we are in fact improving our 1/f noise by combining, using the 4-way combiner here. Look at that. That's a big improvement. 6 gigahertz, again, for this case, we don't really see it, but that's because we're driving the first stage incorrectly. Intentionally in this case, just to show the effect of that AM to PM. So now we're going to pull him out of that region. So look what we did now. We significantly reduced the input power into this part to be consistent with what we did in parts 1 and 2. All right, you'll recall these power levels are very similar to what we've done in part 1 and part 2. So we comparing again apples to apples for the first stage. He's outputting plus 12 to plus 21. We're going to attenuate that now before we go into the 4 combined amplifiers. So now, after the splitter, we're coming in about -2 to 7, roughly the same range here. We're trying to get about the same range. Notice they're still going to be on the tail end of this curve. Plus 7, this will be the worst case. We're just going to start to get into the peak of AM to PM distortion, but we definitely don't go through that region. We're staying on the low side now. Again, a little bit different way to compare the two, but here you see what we started with no padding, okay, versus we used 8 dB of padding now, and we reduced the input power range. So we went from 0.4 to 11.5 to -5 to 6. Big change in input power. Plus, we've changed the input power into the second stage from 10 to 17 to -2 to 7. So again, we brought that way out also. What happens? Again, at 2 gigahertz, these again, just follow the lines over. About the same. I could keep going here. All right, at 2 gigahertz, I don't have to use this input power range or that 8 dB pad. So I'm intentionally, if you will, limiting my performance by limiting my input power, but I'm doing this because I'm more concerned about 6 gigahertz right now. So I have to make a compromise between a 2 gigahertz performance and 6. But you can see there's certainly no real penalty if we operate at what I call the best P in here, which is about +6. We're very consistent between the two scenarios here. But now let's look at 6 gigahertz. So again, we're reducing our input power range. We're putting an 8 dB pad. We're reducing the input power into the second stage to again be on the smaller signal side of this AM to PM distortion curve. So now let's see what happens. All right. Well, you can see right off the bat, we've got significant improvement pretty much across the board. We've gotten this first stage out of that high AM to PM distortion region. We're operating on the front end, if you will, of that curve. And look at the improvement that is possible by just changing the operating point of that amplifier. Notice here, we're not really taking a hit in output power. I mean, if I operate at what we're calling best PN, I'm still getting almost a half a watt out of this amplifier. So I'm not really taking a hit. That's a pretty high power level for any mixer. I can put a pad and I can adjust that output power to anything I need that's less than that. So because we're still seeing some compression effects, my output power is not going to vary by that much, and that's important to note. So this is really a big improvement. Now, can I go back? Is 8 dB the absolute best I can do? No, this requires some experimentation. Maybe I raise that power a little bit. Maybe I change the input to this to keep him on the low side, and I put those amplifiers in the parallel combination on the compressed side. So these are the kind of trade-offs that you need to make and take the measurements that support those to come up with an optimum configuration. But right now, this isn't bad. If you notice, at 6 gigahertz, this happens to be the highest power level. We did 5.4. If we go back to 6. So in this case, I really don't need an equalizer. Okay, I have plus 10 dBm out of my synthesizer. It's fairly flat from 2 to 6 gigahertz. I put a 4 dB pad, and I'm good, right? I can utilize this configuration as is to achieve kind of the optimum additive phase noise performance. And I did that by careful selection of input power into my first stage and by controlling the input power into my cascade. So if you really think about it, if you can have an arrangement like this, if you can afford the power, the DC power, a single driving a combined will always be better than a single driving a single. And if you select the right input powers and you select the right padding. So it's a great way to show how you can demonstrate, again, a wideband amplifier cascade that achieves optimum additive phase noise performance in your system. So again, this was a short one. I skipped a lot. I did that. For those of you that watched part 1 and part 2, thank you. Your reward was a short part 3, but I think what we've shown here is very significant. So please go back, watch it again, and understand what you can achieve by proper combinations of input and output stages. So again, here are the references. Again, contact our applications department if you can't really make this out on screen. We'll be more than happy to send you a copy of this. And again, thank you for your attention, and thanks especially to those of you that have watched all 3 parts. So thanks again, and thanks for watching.